Oh, good. Good morning to all, and welcome to the second session on the Camelot years from 1900 to 1930, an extraordinary period in physics. I think it's probably the most audacious and revolutionary period in all of science, but there might be some argument on that one. I want to thank Debbie and Christine who helped make this happen. And just emphasize that it is on YouTube, so you can see it again. And my daughter watched last week's, so I know it works, and that's up to Alaska. My son so far hasn't watched it, and he's in Halifax. Anyway, so YouTube is another option if you miss them. Now, last week was an introduction to lay out where we wanted to go with the series, but also to highlight Henrietta Lovett, that remarkable woman who transformed astrophysics because she provided us with a tool for measuring distances far enough to measure the distance to other galaxies. That was an extraordinary leap forward, without which the subsequent work wouldn't have been possible. So, and she was a fascinating character. So you might want to just look her up on the web. It's really quite an interesting biography. Now this week, we'll pick up where Henrietta Lovett left it. There was some overlap from last week, but now we're talking about the expanding universe. And not to gobble up the whole talk in a sentence, but if the universe is expanding, it must have been very much smaller at some point. And if it was small, that was perhaps the beginning of the universe and the beginning of an idea, the Big Bang, for which, in my view, there's now overwhelming evidence to support it, some of which we'll talk about today. Next week, it could be it will be quite a shift in gears because these first 2 weeks have talked about the cosmos written large, the universe, and then we move to the atomic and subatomic world, sometimes bizarre, bewildering world, and it has been a venture for me actually to learn a fair bit about it, but it's an important one, and I'm going to try to include with that important biography about certainly Einstein, but Max Planck, who are really the fathers, if you like, of quantum mechanics, reluctant fathers, I might add, and then at the end of today, if time allows, I'm going to include a puzzler and pose some questions to you. That information will be on the website, so you can pick it up there and download it. But some questions to, there's a part 1 for this week and questions, and then there'll be part 2 next week. So things to think about. So here's today's topic, but to frame this, now what is happening here? Here we are. We're all on a journey and of some sort. And last week, I showed you 3.8 million-year-old footprints from an australopith. And we wondered then whether these bipedal ape-like creatures had the imagination, even the interest, to look up in the sky and try and imagine what their world was all about. Probably not, but it's quite different this week because we're looking at, so some of you may have caught this with the BBC News and the latest issue of Nature, the discovery of footprints in the Arabian Peninsula. Now, Arabia 120,000 years ago was very, very different than it is now. Now it's mostly desert. Then it was lush, thousands of lakes and lush vegetation, and a hunting ground for footprints and fossils, if you like. And so you're looking at It's actually the same image, but on the right is the actual footprint in the lake bed of a modern human, and that's unnerving actually, to look at a footprint of somebody who would have had the imagination to look at the heavens and to wonder about some of the questions that we wonder about today. The picture A there is really a superimposed pressure analysis, and you can see that most of the weight was on the heel and the forefoot, and especially the first and second metatarsals. So this was somebody who was erect, freely bipedal, and of course we don't have the rest of the skeleton, but we know that, or at least we have good reason to think, perhaps it was a Neanderthal, but more likely a modern human. So let's just move along. That was then. Now, one thing I want to mention here is that sometimes there are unanticipated outcomes in science, and that most iconic of scientists, Einstein. Einstein in 1915 developed this general relativity, really looking at the relationship between mass and time and space and gravity. So it's a very comprehensive look at how the universe worked. Paul Dirac made an interesting comment about Einstein and science in general. And the comment was that, you know, even the best work by some of the very best people, if they hadn't done it in their day, somebody else would have done it within a few years. That was certainly true of Watson and Crick and the discovery of the double helix. They were lucky. They got in there first. And but there were at least 3 competing groups that if they had faltered, they would have won the Nobel Prize and got the credit. But Paul Dirac makes an interesting point. He said, every once in a while, somebody comes along and he does something so unusual that it might not have been discovered in 100 years, maybe 200 years, maybe longer. And that applied to general relativity. So we're going to be talking about that, I think, in the 4th or 5th session. But even the master who created the equations, the environment for that hypothesis, doesn't always foresee or want to see what the implications of their work was. For example, Einstein believed in a stable universe, like his predecessors, like Isaac Newton. And so did a lot of people, the majority of people. But as you'll see in a moment, others looking at those same equations came to different conclusions. But the equations actually predict an unstable universe and one that was expanding. The other thing that Einstein was aware of was that anything massive in the universe, something sufficient to disturb the space-time continuum, can bend light. And so sometimes you can see stars or even whole galaxies that are otherwise hidden behind galaxies or another sun because the light from that source is bent around that heavy mass. And I'll show you that. Now, anyway, Einstein was aware that that was an implication of his equations. He thought that, that the effect would be so minimal, or at least the devices of the day wouldn't be able to detect it. Well, it was. It got a Nobel Prize 2 years ago. So we're going to talk about that in a moment. His equations for general relativity also predict a black hole. Because after all, if you think of a golf ball and hang it in a handkerchief and make that golf ball dense enough, eventually that handkerchief is going to fold up and close over. That's the formation of a black hole. If you get enough dense, enough mass to do it, to bend that space-time continuum. And of course, at that time, no one was aware of dark energy and dark matter. So anyway, well, here's gravitational lensing. It's quite a nice, clear slide because in the middle, you have a massive object and a gravitational field, that blue thing around it. And on the left is a star in this case, blanketed by that massive object in front of it. But because that object in the middle is so massive, it's capable of bending the light coming from that otherwise hidden object around it so that we on Earth can see it. That's called gravitational lensing. And sometimes it's quite spectacular because it isn't, the lens isn't made up of just one sun or one star. It might be made up of one or more galaxies. And yet the effect is the same, to be able to see otherwise hidden galaxies or stars beyond that galaxy because of the bending of the light. By the way, I chose this slide too because it shows that fabric of the universe, the space-time continuum, and how warped it is by that galaxy. So it's like the trampoline and something heavy sitting on the trampoline, and it's pushing down on that trampoline and bending space-time, changing time and changing space. So that's a beautiful implication or derivative from those equations for general relativity. Well, let's go back to an earlier period, actually a couple of years just following Henrietta Leavitt's pivotal study in 1912. So 2 years later, and running up in the early 1920s, this interesting fellow, Melvin Slipper, measured the recession velocities of 40 nebula. Now, nebula in those days were things that, well, they were nebulous. We didn't know that they were galaxies, but we certainly had, or at least they thought, they were certainly distant. And he used the Doppler effect. Now, that's an interesting tool. And I'm going to say a little bit about that right now. The frequency, if you're standing by still in a street and a truck approaches you and comes towards you, aside from the noise, the loudness increasing, the frequency of the sound increases. If that were light, that would be blue shifted. As the truck passes you and then begins to recede in the distance, the frequencies become slower. That's red shifted. All right. So when one speaks about stars or nebulae or anything stellar object out there as red shifted, it means it's moving away from you. Or in the case of Andromeda, our nearest neighboring galaxy, it's blue shifted because Andromeda is due in several billion years to actually merge with our galaxy. Okay, so that's the Doppler effect. So, so here's a fellow speculating well before others about, well, it turned out he was right. So moving on, and this interesting person, Alexander Friedman, a Russian scientist, and he's looking at Einstein's equations for general relativity and realizes that one of the outcomes of the equations was that the universe was expanding. And he even goes so far to suggest that, well, it's expanding, it must have been a period when it's very much smaller, but also much denser. Now that's really key, dense and small. One of the side notes, unfortunate ones, that his paper was largely unnoticed, except by Einstein, too late. In 1933, it was 8 years after he died, or Friedman, of typhoid fever. So I included him. So here we are. Now we come to really quite an interesting character. A young Belgian Abbé, Georges Lemaitre, trained in theology and physics. And he has a PhD, had a PhD from MIT. So he knew what he was talking about. And when he heard about Hubble's early findings, and I'll say a bit more about that in a few minutes, but the early findings were that these nebulae out there, including Andromeda, were other galaxies.
Garlic powder.
And they were moving away.
Garlic powder.
And so he suggested that the receding velocities of extragalactic nebulae, or galaxies,
I'll look again,
were a cosmological effect of the expansion of the universe. That's really important. Is that the universe isn't kind of a set bowl of jelly, and these galaxies are moving in the jelly. It's the jelly that's increasing in size. It's the universe carrying the galaxies apart. That's what's actually happening. And then he had one of these unfortunate effects. He, I think I mentioned last week, he gave this information to Albert Einstein, whose response to it was that, the mathematics might be all right, but the physics was terrible, and dismissed him. Sir Arthur Eddington was one of the most influential astronomers of his day, and Lemaitre gave him his paper. And guess what? Eddington lost it. So there was no feedback from somebody with Eddington's influence to kind of push it along. So, and that happens. I mean, there's another story about J.J. Thomson, who is the head of physics at Cambridge around the turn of the century, and he got a Nobel Prize for discovering the electron in 1897. And Niels Bohr, who's a huge figure in this 6-week story, was on a 1-year study leave to the UK and went to Cambridge and was going to study under J.J. Thomson. And Bohr had this intriguing hypothesis for what the electrons did. It turned out he was right. And he gave the paper to Thomson, and it sat on his desk, and it sat on his desk, and it sat on his desk unread. And finally, Bohr tired of this, and he headed off to Rutherford, who was in Manchester at the time. That relationship between Rutherford and Bohr is a really keen one to next week's story and the week after that. People and things are ignored. They get lost. They're unread, and those are tragedies. So Edwin Hubble, a very interesting person. So in 1922, using Henrietta Leavitt's techniques for measuring the distance to nebulae and stars in the nebulae, showed that, well, gee, the distance to Andromeda and these other nebulae were just too far away to be included in the Milky Way. So there had to be more than one galaxy, more than one Milky Way. Wow, that just expanded the universe hugely. And then in 1929, or through the mid-20s, but 1929, he showed that these nebulae, except for Andromeda, were moving away from the Earth. And the further they were away, the faster they were moving. And so Hubble provided the experimental evidence for what Lemaitre had suggested on a theoretical basis, based on general relativity. So we have theoretical evidence, we have experimental evidence. I don't think Hubble really understood the moment or the importance of his observations, because if he had, he would probably have won a Nobel Prize for the Big Bang. I might say if Einstein hadn't been so stubborn about his equations for general relativity and Lemaitre and others' interpretations of them, he might have shared that Nobel Prize, or perhaps won it and beat them all. He did the opposite thing. He was so stubborn about this business that when Lemaitre and others told him that, look, the evidence from his own equations suggested that the universe was expanding, he introduced his cosmological constant into the equations to actually correct it and return it to a relative, stable, fixed universe. He was wrong. And interestingly enough, in 1931, he publicly acknowledged that he was wrong on the basis of Hubble's work. By the way, there's Edwin Hubble at the 100-inch Mount Wilson Observatory, the telescope, and on the right is a color picture, shows you more of it. But you can see that Hubble was an athletic person, very quite handsome, charming, Rhodes Scholar. He read law at Oxford because of pressure from his father, but then became very interested in astronomy, and very clever. And it was something for a young man like him to be able to capture this 100-inch Mount Wilson telescope and to have almost exclusive control over it, because it was the biggest tool on the street in astronomy at that time. So he was very fortunate. One unfortunate characteristic of Hubble was that he bragged a lot, and he always seemed to have this impulse to enlarge on his achievements, which were considerable anyway, but it was somewhat irritating for people. Now, the Hubble Telescope, probably the most famous, well, not probably, the most famous space telescope is the Hubble Telescope. This is the 30th anniversary in this year. And if you look at that thing in the center, that's a galaxy, and not unlike our own. And it was quite an achievement. And there's the telescope itself. You may remember the controversy of this, because when it was first launched, it didn't work because there were defects in the mirror. So everything was blurred. So they actually had to have a space mission scheduled, and astronauts travel over to the satellite and fix the mirror. And they did. And then all of a sudden, the images became perfect. So, and the story went on. I mean, there are so many firsts for this Hubble telescope. It's amazing. Isn't this wonderful picture? There's the 100-inch telescope that Hubble worked with. In the middle there is Hubble, and you'll recognize Einstein on the left. I don't know who the other men are, but anyway, there they are. That was the day that Einstein publicly apologized and acknowledged his mistake, withdrew his cosmological constant, and believed in an expanding universe. So big people make big mistakes, and it's what they do with them that counts. So here's another interesting story, because can't see all of that, but I would see enough. You may remember about a decade ago, there was a lot of buzz about the cosmic background radiation. And I think even local newspapers as well as the national ones, had pictures looking exactly like this. And what are we looking at? We're looking at an uneven pattern that's related to temperature of the whole cosmos, the universe. Now, of course, it's not a circle like this, but it's but the whole universe in all directions has this kind of little patchy, uneven pattern, and that's related to the temperature. The temperature. We're looking at radiation that escaped the universe, or at least became visible, about 300,000 years after the Big Bang. Before that, the universe was a seething, intensely hot, crowded environment of ions, what we call plasma, and so of, in that case, hydrogen atoms and some helium atoms, but that was about it, and a sea of elementary particles. But as time went by and as the universe continued to expand, it cooled. Well, it cooled to around 4 to 5 degrees Kelvin. That's pretty cold. The very fact that those temperature differences are there are the reason why we're here. Why? Because the earliest matter was unevenly scattered, just a little bit. And with dark matter around, we still don't know what dark matter is, but it certainly adds mass to the universe, and therefore gravitational effects. And with an uneven dispersion of matter like this, dark matter could begin to impose its will and begin to pull this matter, some of this matter together into clumps. Those clumps became future galaxies and stars within those galaxies. So that's the beginning of, in a few words, of the beginning of the universe in that first 300, 400,000 years, maybe out to 500,000 years. Now, there's a lot of this story because there were two people, Penzias and Wilson, and they were working with a very sensitive instrument for recording electrical activity in the radio band. And it was one of a kind device, super sensitive, and they had other ideas for its use, and they were totally frustrated because they couldn't get rid of this background buzz or hum. And they thought that they checked over this device again and again, looking for sources for this. Could it be coming from the neighborhood? Some other source. Couldn't find a thing. So they had no clue where this extra noise, hum, buzz, was coming from. Well, they apparently were unaware that work back in the 1940s suggested that a Big Bang would have created radio waves that could be picked up to the present time. At a meeting, Penzias and Wilson got together with Dick and Peebles. By the way, Jim Peebles, won a Nobel Prize last year for his work on the early universe. So we'll touch on that. Well, Dick and Peebles knew exactly what it was. It was this background radiation left over from the Big Bang. Guess who got the Nobel Prize? Not Dick and Peebles, not the people who originally developed the hypothesis, but Penzias and Wilson, who had no clue what they had seen. So it was one of those interesting comedic moments in physics and science. In fact, the story goes that Penzias and Wilson found out about winning the Nobel Prize in the New York Times and also found out why they won it. So interesting story. The reason why this sea of radio waves that are emanating, the light quanta, they were trapped in that sea of ionized particles and nuclei. But as the universe cooled enough, then electrons could join protons and neutrons and form atoms. Now the photons of light were able to escape. That's what created the light, which, because it's coming from a long distance, was manifest here as radio waves. After this period, the universe goes into a period of darkness. And so that's the point I wanted to make about the expanding universe and galaxies moving apart from one another. It's because of the universe itself expanding. It's not because the galaxies are moving within the universe. So here's, I'll tell you, I think I've seen about 15 or more drawings to illustrate what happened with the Big Bang. And almost certainly it didn't look like this megaphone. It's probably much better to think of this as something very central and expanding in all directions. But then how do you create a figure like that to illustrate it that way? So, but it does illustrate that you see that blue blotchy stuff, that's the cosmic background radiation we've just been talking about. Then the universe goes dark, and you can see that kind of middle size there. Those little wavy things are the radio waves emanating in all directions in the universe. And then there's a period, 100, 200, 300,000 years later, when the dark matter does its thing and begins to clump other matter, and the first galaxies and stars appear. So, and here's another one of those wonderful, well, not so wonderful illustrations. So we'll just move on from that because I think they're misleading. Now, what happens when, I'm going past the 1930 now, obviously, because I want to tell a little bit of a story here, but where did these first galaxies and stars, how did they actually develop? Well, as I mentioned, dark matter created a gravitational effect, and which tended to clump whatever matter was there together. And then it began to spin. And as it began to spin, it flattened. So instead of an orb, it became a flat disk. And at the center would be, for example, a star, a large star. And then well, not in those early days, but in later times, planets were to form. They formed further out. So, and here's what, I mean, all of this is imaginary stuff by artists directed by a physicist, or what it might have looked like, but here's one of those stars. One of the interesting things, why do we know about the Big Bang? Because, or at least what's the evidence for it? Well, one of the strongest pieces of evidence is that stars have evolved. Our sun, in our region of the universe, in our galaxy, is the third generation star in the area. So there have been two suns before us, not necessarily in exactly the same place, but in the neighborhood. And so there have been generations of stars, and they've matured. They've become, like biology, which I'll remind you of in just a moment, they've become more and more complex. So in the beginning, stars were made up of entirely, just like a bag of hydrogen nuclei. And gravity began to compress it, and it became more and more dense, And as it became more dense, finally the temperature and the pressures rise to the threshold where nuclear fusion occurs, where hydrogen nuclei actually combine to create helium with the release of an enormous amount of energy. That energy is, amongst other characteristics, includes photons of light. That's when stars turn on. The switch went on. So you might have seen this big ball out there, or you wouldn't have seen a big ball out there, but until fusion took place, the stars had not lit up, okay? Now, in later generations, what happens is that gravitational effect, there are really two forces working at opposite ends. All the mass of the star is compressing all of that material, and mostly hydrogen in the earliest stars, okay? Compressing, making it smaller. But once fusion starts in the core of the star, and with the release of all of that energy, now you have a force expanding the star. So the two are in some sort of balance. And the photons of light are released by the star, and that's starlight. So just moving on. Now, one thing I want to point out is that it's stars have a birth, they have a middle life, and they have a death. And for the large and middle-sized stars that are capable of creating enough pressure and high enough temperatures, by combining progressively higher atomic weight elements, can create all of the elements up to iron. And that's it. Beyond that, when you try to combine iron atoms together, nuclear fusion is not only almost impossible, but there's a net energy loss, meaning it takes more energy to create the combination of two or more iron nuclei than energy created. Now what happens is that expansile force now becomes a diminishing force, and the star begins to collapse in on itself. And it eventually becomes very, very dense. The temperatures and pressures become enormous, and it explodes. That's called a supernova. In that supernova event, the temperatures are high enough, and now the pressures are high enough to begin to fuse even the heavier elements and to create the elements for the rest of the periodic table. Now, not quite for gold and platinum. That requires the fusion of neutron stars. But that figure that's kind of hard to see on, well, it's in front of you right there, but you see that Fe in the middle, about in the middle there, that's iron in the core of that star, but going through a series. So that's the progression. Now here's the periodic table. I put it up here because it's interesting in itself, but I thought you should see where the elements of life sit in this periodic table. And there are two things about them. They're all relatively light and small. So the number I have in the brackets are the number of electrons or the number of protons, both the number of protons and the number of electrons for that element. And nitrogen has 7, oxygen 9, sulfur 14. Now, what's the importance of that? Because in 2 weeks, you're going to find out that the electron orbits can contain only so many electrons. 2 in the first orbit, 8 in the second. Now, if you look at carbon, it means It has enough electrons to fill the inner orbit, but it's too short. It has a debit of 2 for the second orbit out. That means that carbon is constantly looking for a partner that can share electrons with it. That's why carbon forms such good bonds with so many other elements, and why I called it the matriarchal element in the story of life. So that's really important, and to show, we'll come back to that, but it's really important. So moving on. So evolution, we think of evolution as Darwin and Wallace, but matter evolves, the stars evolve, the universe evolves. That includes the evolution of elementary particles and the fields that are associated with them. The simplest ions, hydrogen and helium, and a bit of lithium at the beginning. Now there are 118 natural elements in the periodic table. They've all been created in the explosions, the terminal explosions of stars, or the merger of stars. So let's just move along here. And the evolution of life. Like the evolution of matter, the inanimate matter, the earliest organic molecules, amino acids, DNA, RNA, moving from the simplest cells to complex cells, to simple multicellular organisms, to much more complex multicellular organisms, to the evolution of a proper nervous system. That's been a work in progress over billions of years. Now I'm changing a little bit here because trying to work in some other stuff too, and this comes out of a question last week. We think now, they think, physicists think, black holes are really, really common. Every galaxy has a giant one in the center of it. And the Milky Way has Sagittarius A. I mean, how big? They have the mass of thousands, even millions, of the mass of our star, of our sun. So they're enormous. This one, but we haven't seen a black star. We can infer black stars, but we haven't seen one until a year ago. And here it is. And because of the symmetry, you know, you say, gee, that looks awful fuzzy. Well, I can tell you this one, from a long, long way away, we're lucky to even see it. The important thing that, or one of the things that interested physicists and astrophysicists when they looked at this is the symmetry of the black hole, which is predicted by Einstein's equations for general relativity. Wow, that's kind of a nice little piece, isn't it? I think. And I included some of these. These are artist simulations, but they're interesting, of a merger of two black holes on the left, and on the right, a black hole literally sucking in a young star nearby. So now, this is what got the Nobel Prize in 1917, because here's an artist's representation of the collision of two black holes, each of them with a mass at least 20 times greater than our sun. And they do a dance around one another. And they come closer and closer and closer and closer, and then they merge. And like me throwing a rock in a pond, it sends ripples out in space-time. Those are called so-called gravitational waves, and which Einstein was aware might happen if such an event happened. And and thought wouldn't be detectable by any device then. But where? I mean, they've been working on this for the last 35 years in the United States. Remarkable when you look at the way the Senate and the House work together these days. We had successive administrations and houses and senates support this program for 30 years. It tells you something about cooperation. Anyway, they found a way of detecting these gravitational waves. And I'll come back. But anyway, this is an artist's illustration of these waves kind of spiraling out from a merger. Here's the device, actually, the one in Italy. This one didn't pick up the original one because it wasn't complete. But how did they do it? Well, rather simply, they had two tracks of equal length and shot a laser beam down each. And you could imagine the precision of this, of these devices. And with the idea that if these gravitational waves kind of swept through this device, it would distort one arm more than the other, and therefore change the time for the laser beam to bounce back and forth in each leg here. That's how they picked up these gravitational waves, and then turned the signal into a sound, or what was called a chirp. And I don't have that sound for us, but there you are. There's what they look like. You can see these kind of waves here. These are the chirps from the merger of those two black holes. Future ones are going to be space-based and probably much more sensitive. They're almost certainly were gravitational waves produced by the Big Bang, but they're probably much smaller now and probably much more difficult to detect, but might be detectable with space-based devices. And that's really important because we're really blind. In the case of the Big Bang, we're really blind for that first 300,000 years because nothing escaped that hot plasma, no signals. So anyway, now, if you have a ring on you and it's gold, it was produced by this device, the collision of two neutron stars. And this was picked up within a year of the first, the collision of the black holes. And by the way, they found a whole bunch of these. I mean, once you find one, you find a whole bunch of these binary collisions of black holes. But here was one, and there have been other ones since, of neutron stars. Neutron stars, you could think of a neutron star as something of the mass of the Earth compressed into something the size of Manhattan. That's how dense they are. And sometimes they collide with enormously high temperatures and pressures, just what you need to create the heaviest elements in the periodic table, including platinum and gold and higher atomic weight elements. So if you have any gold on you, that's the birthplace, and what some people have called stardust. So we don't need to talk about that. I do want to, how are we on time? Yeah, it's just running a little short. I want to say something about this because Penny Lynn Cookson and I are going to be talking about in another series the relationship between art and science, which I happen to believe are quite close, even if it doesn't seem that way sometimes. But it's probably closest in physics. There is a strong feeling, and certainly Einstein felt that way, and many of the theoretical physicists have felt that if the equations to explain a phenomenon were elegant, if they were simple, if they were highly predictive, they were more likely to be right, and they're beautiful. So that's beauty as seen. And when Einstein talked about beauty in the universe, he was really talking about the natural laws and the order of the universe, all of that on an awesome scale. So now I've made this up. I took the most important of this group of physicists, from 1900 to 1930, and I graded them with how were they superior mathematicians, middling ones, or not, and something else, something that I think is maybe more important than the math, is this ability to visualize in your mind, to somehow see relationships beyond the math. Niels Bohr was incredible that way. Not a good mathematician. Einstein was a master of visualization, a better mathematician than Niels Bohr. But you look at Heisenberg, superior, I mean, right at the top. And his boss, Born, at the bottom, really gifted mathematicians. And one I'm a big fan of, the only experimentalist in that group, Rutherford, from Cambridge in England. I think his math is pretty basic. But in the visualization world, this guy had it. And so I just wanted to leave you with those thoughts. And we'll talk about other things later, but have we got just a few minutes? Okay. One other thing. This is the puzzle for you to work on. By the way, that's a group that I worked with. That's at one time. So that's my little group of physicists. Notice there's only one woman there, and she was probably the best of us, as it turned out. So anyway, I wrote a piece. So go to the web. It'll be on the website, right? Yeah. Well, I don't want to read it out here, but get this piece from the website. It's consider the consequences. It's really something about foretelling the future, and what are the options for the future. And there are really, I think, 5 options for the future, based on what we know about the universe and what we know about life now. And so you can look at those options and see what your response is, and then maybe we can talk about that next week. So it's a little more interactive. And that's part 1. And part 2 will come next week. So we'll see where that goes. So I hope you enjoyed this. I did. The stuff is pretty exciting. So we'll move on next week to this whole other world, this strange world of the quantum. And the 2 fathers of quantum physics. Max Planck and Einstein, and a fair bit about the biography of the 2 men. They couldn't have been more different, but they became best friends. And so I want to say something about that, particularly in our polarized world these days. So goodbye, and we'll see you next week. Thanks very much. Good.
Should we do any questions?
Oh, questions.
Yes, can you hear me? We can open it up briefly for some questions. You can either quickly type them into chat. I don't see any right now. Or does someone have something that they want to ask directly? We could probably manage that as well. Anybody have a question?
Or another option would be to submit it, and then I can read it out and answer it next week.
So that
Yeah,
actually
that's
is,
fine.
hang on a minute, I'm just going to turn off my speaker.
Just don't ask things that are too difficult.
That actually would probably work the best if you didn't hear Dr. Brown. If you want to submit a question, you can email it to me. You have my email. I sent you all of the links, so just attach it to that. And I will get that to Dr. Brown, and he can address those questions next week, probably
Yeah.
more thoroughly than you would
Yeah.
want, you could do right now.
Yeah, you mean I could
So,
look it
and
up.
it'll give you some time to think and craft a question for him.
Okay.
If that's okay, that's, I think, how we'll leave it. And I will email you that document directly that
Okay.
you were referring to.
Yeah, I'll send it.
I will send that to all of you that are here today that have registered, and then you can see what that's all about.
Okay.
All right, so if there's nothing else, I'd like to thank everyone for joining us again this morning. Thank you, Dr. Brown. Thank you, Christine. And we'll see you here again next week, same time, same place.
Okay.
Bye, everybody.
Bye-bye.